Hello, this is Opti471B, Lab Group 5B. In this lab, we use a Shack Cube interferometer, which is conceptually similar to the shear plate interferometer, with the only difference being that the shear plate interferometer interferes a wavefront with itself, whereas the Shack Cube interferometer interferes an aberrated wavefront that is nearly perfect. The fringe visibility is based off of these equations in this diagram, where the fringe visibility is proportional to the square root of both intensities multiplied with one another. The total of fringe visibility is given by this equation, where if we get maximum fringe visibility if we set the two intensities equal to one another. We do this by setting a polarizer when we have the mirror here. However, it is worth noting that we can't get 100% fringe visibility in this case because the polarization of the laser decreases with each element that it passes through. In this case right here, we don't need a polarizer due to the fact that we have 4% reflection off of both lenses.
Why use a polarizer with a test mirror? From the Fresnel equation, we know for a lens there's about 4% reflection at each surface, and for a mirror there's about 98% reflection. Therefore, we need to match the reflected intensity from the mirror and the reference lens to get maximum contrast of the fringes. We know the laser is linear polarized, so we can use a linear polarizer to cut down the intensity from the reflected beam from the mirror. If the degree of polarization at this point was low, we could also use a neutral density filter.
It is worth noting that the radius of curvature of both the lens and the mirror is located at the pinhole source, which produces two pinhole patterns located just at the other side of the beam splitter, where the pinhole would be located. It is also worth noting that the reference lens was made with super high tolerances.
An important aspect of this lab is to observe the resulting interferograms of different combinations of aberrations. Here we have tilt and defocus, where A is no tilt, no defocus, B is only tilt, B is only defocus, and D is tilt and defocus. Here are the spherical aberrations. As you can see, it appears as centered concentric circles when tilt is not present, but when tilt is introduced, the circles become off-axis. Here is Coleman tilt, where the 3x3 array represents the impact of tilt when either in the positive or negative direction in the x and y axis. Here we have coma, tilt, and defocus with the similar 3x3 array. Here's astigmatism, tilt, and at sagittal focus. Here we have astigmatism and tilt at tangential focus. Here we have astigmatism and tilt at medial focus, and here we have astigmatism and tilt at Petzval focus. In order to quantitatively evaluate these interferograms, we use the least squares method explained by Wyans. The basic gist is that you first get the data in terms of the fringe position, as can be seen in the top right corner. Then you normalize the data so it's symmetrical and displaced according to the shear. Then you plot this as a best fit polynomial, and then you use the coefficients a sub 1, a sub 2, a sub 3, and a sub 4 to solve for the various aberration coefficients.
This is lab 9. We use the Shack Cube interferometer. This is the setup for using a mirror. The key thing to know is there's a polarizer in between the beam splitter and the test mirror, which is over here. This is the null fringe with the test mirror. There are about 1 to 2 fringes present. As we added defocus, we noticed that the fringes became more abundant and they were more tightly spaced for before and after focus. As we added tip tilt, vertically or horizontally, the fringes became off-center with respect to the tip tilt we were doing. When we added tip tilt and defocus, we expected a summation of tip tilt and defocus in the interferogram. This is a test setup for the testing a lens. Here's the lens, here's the Shack-Hartman cube, this is our viewing screen, here's the microscope objective and the pinhole, and here's the reference lens glued to the beam splitter. This is the null fringe for the test lens, and as we added defocus we observed the same effects as with the test mirror. When we added tip tilt, vertical or horizontal, the fringe pattern became off-centered vertically or horizontally depending on the tip tilt adjusted, as shown in these two interferograms. And when we added tip tilt and defocus, we expected a combination of the above, which is what we kind of see here. From this, we were able to obtain the following data, and we were able to perform a least squares fit, and it resulted in the following wavefront coefficients. Some observations noticed were that the tip tilt mounts used were coupled and added a slight defocus effect on the fringes, and as we moved through defocus, it caused the fringes to become off-center even when the tip tilt was removed, and this could be avoided by using higher quality equipment. And to help align faster, one could align the focus dots on the back face of the beam splitter cube.